Thermal analysis. This is another characterization technique for solid materials. We just heat the solid materials inside the instrument and we study the changes which takes place during heating. And there are different techniques in thermal analysis: DTA, DGA, and DSC. We will study these techniques. The thermal analysis method, what is the advantage of thermal analysis method? Thermal analysis method investigate the properties of the solid. We can study by thermal behavior of the solid, we can study the properties of the solid. Either solid is stable, unstable, what is the effect of heat, what type of products are formed, when up to which temperature it will be stable. So the properties of solid can be studied by thermal analysis method as a function of change in temperature. We increase the temperature or either decrease the temperature, and we study the properties of the solid, thermal properties of the solid. Thermal analysis methods are useful for investigating phase changes. Phase changes mean conversion of solid into liquid, liquid into gas, and these type of changes. Decomposition can be studied by thermal analysis method. Loss of water or oxygen will take place among samples, and for constructing phase diagrams, we can use thermal analysis methods. There are different types, different techniques used in thermal analysis method. We have previously seen DTA, DAC, and DGA. So first we will study about DTA. What is DTA? DTA is differential thermal analysis. A phase change produces either an absorption or ablution of heat. For example, when we convert the liquid into gaseous form, convert a liquid into gas, absorption of heat takes place. While the opposite of this, that is conversion of gas into liquid, absorption of heat takes place. So in any phase change, there is always either absorption of heat or ablution of heat. It is either exothermic or endothermic. So what is done in DTA? In DTA, the sample is placed in one chamber and a solid that will not change phase over the temperature range over the experiment in the other. We will take two chambers and we will take a standard and put the standard in one chamber. The standard will not change the phase when it is heated, while our sample will change the phase it is put in another chamber. Both chambers are heated at a controlled uniform rate. That's the increasing of temperature at uniform rate. It is heated in a furnace, and the difference in temperature between the two is monitored. For example, if our sample is absorbing heat and the standard is doing nothing, it is not absorbing and not emitting the heat. So our sample is absorbing the heat. Our sample temperature will be low as compared to the standard. And due to this temperature difference, we can calculate the amount of heat absorbed during the endothermic reaction. And in the same way, if it is exothermic reaction, the temperature of sample will be more high as compared to the temperature of the standard, or the standard will not change the phase. And from this difference of temperature, we will be able to calculate the heat released by the sample. So this is the basic principle of differential thermal analysis, in which we calculate the heat absorbed or evolved during a phase change. Any reaction in the sample will be represented as a peak in the plot of differential temperature exothermic reactions, as a peak in the plot of differential temperature. Here is on the x-axis is temperature and on the y-axis is temperature difference. This is the graph for this is the DTA diagram or DTA graph. DTA for the trace of potassium nitrate. So here we obtain 3 peaks, and 3 peaks are in downward direction. First peak is showing tetragonal to trigonal. First, when we heat the sample, this peak towards down direction, it shows that it is endothermic reaction. Temperature is decreasing. So one crystalline form of KNA3 changes into another crystalline form, and this is endothermic reaction. So here peak is obtained at this temperature, that is 100 degrees centigrade. When we reach 300 or somewhat more than 300, another peak is obtained because here melting of KNO3 will start. And melting is also an endothermic, so peak in downward direction will be obtained. Here a third small peak is obtained when we, after melting, when we increase further temperature, and what will happen, decomposition of this KNO3 will take place and it will be above 500 degrees centigrade, 550 degrees centigrade, above 550 degrees centigrade decomposition of the sample will start. So in this way, in DTA instrument on the screen, this type of graph is displayed from the data which is collected by the instrument. And from this graph, we can mark different peaks and we can manipulate due to what reason these peaks are obtained. So this type of DTA will give information about the thermal behavior of the materials. Before melting, what takes place, and after melting, what things takes place, what is the melting point, at what temperature it will decompose, at what temperature it will be converted from tetragonal to trigonal form. All information we can get from this type of DTA diagram. Exothermic reaction give an increase in temperature and endothermic give decrease. You know that. So the peaks appear in opposite direction. So when there is exothermic reaction, the peak will be in upward direction. Here all three reactions are endothermic, so peaks are in downward direction. So the conversion from tetragonal to trigonal takes place at temperature 129 degrees centigrade. Melting takes place at 334 degrees centigrade, and decomposition takes place at 550 degrees centigrade. Another technique of thermal analysis is thermogravimetric analysis, which is also called TGA. In this experiment, the weight of the sample is monitored as a function of time as the temperature is increased at a controlled rate. Temperature is increased at a controlled rate, and with the increase in time, we will monitor the weight of the sample, because uh, when sample is decomposing, its weight will decrease with time. So in this instrument which is used for thermogravimetric analysis, that instrument is called thermogravimetric analyzer. So in thermogravimetric analyzer, the weight of the sample is monitored with the passage of time, and the temperature is increased or decreased at controlled rate. The loss of water of crystallization or volatile such as oxygen show up as a weight loss, as does the composition, as does decomposition, oxidation or adsorption of gases show up as weight gain. So some type of changes can be there which will cause weight loss, and some type of changes will cause the weight gain. So due to what reasons the weight loss will take place? If there is water of crystallization, when we increase the temperature, water of crystallization is lost, oxygen is lost. So due to this, the weight of the sample will increase, and due to decomposition, the weight of sample will decrease. But when there is oxidation, adsorption of gases, the weight of the sample will increase. Small weight loss up to about 550 degrees centigrade, probably due to loss of absorbed water, followed by a dramatic weight loss when the sample decomposes. This graph for a sample shows that here on the x-axis is temperature and on y-axis is percentage weight. And we have previously seen that in the DTA, on the x-axis was same temperature, while y-axis was different. On the y-axis was temperature difference. DTA is only used for phase changes, but thermogravimetric analysis can give information about decomposition, oxidation, loss of water, and give other information also. So here is weight is 100%, percentage weight is 100%. When we increase the temperature, weight loss take place. And here the weight loss takes place due to loss of water molecules. And a sudden weight loss here takes place due to decomposition of the material. So from this graph, TGA diagram, uh, we can obtain the detail that at what temperature the sample will decompose. At what temperature it will remain stable. Up to here, up to 500 degrees centigrade, it will remain stable, and above 500 degrees centigrade, it will decompose. The third technique in thermal analysis is differential scanning calorimetry. Differential scanning calorimetry is also called DSC. DSC measures the amount of heat released by a sample as the temperature is increased or decreased at a controlled rate. It also measures the amount of heat released by the sample when the temperature of the sample is increased or decreased at a controlled rate in the furnace. And so we can investigate chemical reaction and measure rate of reaction for phase changes. We can study various chemical reaction, and we can study exothermic, endothermic reaction. We can study phase. We can use it also for phase changes, study of phase changes. Here is the diagram of DSC. On the x-axis is temperature, and on the y-axis is normalized power. So first diagram A is DSC trace for the melting of indium metal. So here melting this downward peak show that the melting point of indium is near 160 degrees centigrade, and decomposition will not take place up to 180 degrees centigrade, no weight loss. And here is the second one is integration of the power data. Here on the y-axis is heat content, and on the x-axis is temperature. So when we increases the temperature, the heat content of the sample increases, but up to certain limit, the heat content will not increase further and it will remain constant. So this method can be used for studying the heat capacity of the material, how much heat a material can absorb.